Hello and welcome everyone. My name is Anil Gupta and I have my colleague over here, Omkar. We are going to talk about Apache Phoenix tuning. So in our presentation, we have made few assumptions. We expect our audiences to have some basic knowledge of HBase and Phoenix. And the actual performance of the improvement varies as per the user's workload because there are so many variables when we start talking about HBase or Phoenix performance optimizations. And due to time constraints, we are only going to cover the most important tuning tips. Like at TrueCar, we have been trying to optimize cluster for and optimize our workload for last 2 years. So in the agenda at the high level, at the beginning, we are going to cover the data architecture at TrueCar, and for what cases we use Apache HBase and Phoenix, and then the performance optimization techniques like cluster settings, table settings, data modeling, and instance types that EC2 instance types that we use in AWS. So around 2 years ago at TrueCar, we started a project called Capsella, where we wanted to migrate our infrastructure from data center to AWS. So as of now, almost like 80–90% of data engineering jobs are actually running in AWS. Currently in AWS, we use CloudBreak to deploy our clusters. And TrueCar is a data-driven company, so we run a lot of ETL jobs to produce data. So if any of you have visited TrueCar.com, the price curve data, the inventory data, the vehicle images, all those data sets are actually the output of our jobs that are either running in MapReduce or Spark. So typically, the input data sets are actually either coming from S3, Kinesis. We use Kinesis for streaming and empowering near real-time workloads. When we use Kinesis for streaming, then we use Spark Streaming to support the near real-time workload. Postgres is our RDBMS. And then we use FTP and stuff like that to get data from our third parties. So as I said, so Spark and MapReduce, both of them are computation engine. And then basically Hadoop in HBase and Phoenix is our Hadoop database. So we do a lot of range scans, point lookups, and stuff like that. We usually try to stay away from joins and then full table scans. So the output of our MapReduce or Spark job is either written to Elasticsearch, Postgres, Redis, S3, or Redshift, depending on the product requirement and customer requirement. So moving forward, so there was one huge change that we made when we started our migration from data center to AWS. So in data center, we had one production cluster that was running Spark, MapReduce, and HBase. So in that case, like if an analyst starts a Spark job that is just looking at our clickstream data for last 1 year, and that data is not in HBase, it's just there in HDFS. So then that ad hoc Spark job would start impacting our HBase cluster performance, and in turn, it will start impacting our jobs that were having business SLAs, like our inventory processing job or image processing job. So and then it was really hard to debug to figure out what is going on this cluster, because if you look at the HBase metrics, you won't see a lot of load, but then HBase is not running at its usual pace. So in that vein, when we started our migration to AWS, we segregated the compute cluster from the storage cluster. And right out of the gate, we saw a lot of improvement. Like we had a lot of reduction in the interference of the resources. So if right now, if an analyst goes onto our compute cluster and runs a Spark job that is just reading data either from S3 or HDFS, we won't see any performance degradation in HBase. At the same time, like HBase is more I/O heavy, like it's meant for really fast reads and writes, while MapReduce and Spark is meant for compute. When we segregated the clusters, we also got the freedom to choose different type of hardware for HBase and MapReduce. My colleague is going to cover more about that at the end of the presentation. And then since we segregated the hardware, we have better consistency and debugging capability to figure out problems in our environments. So the typical use cases for HBase and Phoenix at TrueCar is TrueCar does a lot of data analytics on automotive data. It's like we have all these price curves, histogram data, and then the historical image data, historical inventory data. So all of that is stored in HBase. And then we also use HBase to store highly unstructured data, like because HBase is a NoSQL. So like we have this image processor job, and then in the image processor data set, a vehicle can have images ranging from 1 to 100. So we cannot just keep on making columns. So we just use pure NoSQL way of writing data into HBase. So for this one, we just use the raw APIs of HBase. Then we have some use cases where our data is semi-structured. When I say semi-structured, like most of the columns in those tables are static, but we have like 1 or 2% of column where they are dynamic, and like they are probably less than 10 or 20. So in that case, we start using dynamic columns of Phoenix. So we use the best of the both world as per our use case. And then we also put some of the data sets in memory. These data sets are very small, like they are like GB or less. We do that so that we don't have to load these data sets redundantly into our mappers or Spark executors. And because it leads to a lot of memory wastage, my colleague Omkar is going to cover about that more in detail later on. And we also try to make sure not to try to use HBase like a analytical system, like try to run full table scans, try to connect it through Hive. We don't try to encourage that. We usually try to denormalize data and then just either do very short range scans or just do point lookups. And in that case, HBase performs really well. So let's start with talking about cluster settings. So this there is a setting in Phoenix which is called update cache frequency. By default, the value of update cache frequency is always. What that means, so whenever we instantiate an object of a statement or a prepared statement, Phoenix is going to make a query to a system.catalog table. It's a system table of Phoenix, and to get the metadata of the table on which we are creating the statement or prepared statement. So let's say if your data and it's very well distributed across the cluster, but you have a application where with a very high read throughput and you are making a lot of statements, like we do that in one of our web service. So in that case, whenever we were creating statement, it would first hit the system.catalog table, and this system.catalog table has single region. So it would create a hotspot, and then the like performance was severely degraded. So once we changed the setting from always to 120 seconds, so basically we told Phoenix to cache the metadata on the client side and only refresh it for every 2 minutes. Once we did that, we saw a 5x performance improvement in some of our jobs. Now let's talk about table settings. So in the table settings, I'm going to cover pre-splitting the table, pre-splitting the secondary indexes, Bloom filter, hints, small no cache, and then in-memory option for the table. So I think one of the most important thing in when we try to set up a new table in HBase or Phoenix is to make sure we pre-split the table. Because let's say if we don't pre-split the table, your table is going to start with one region, and as we all know, like HBase is a distributed data store, and if we don't pre-split the table, it's going to start with one region on one region server. So then it becomes like a monolith system. So let's say if you have a new table and you start populating that table with 100 mapper from the beginning, those 100 mappers are just writing data to one region server. And in that case, you are going to see a really, really bad performance. And that leads to a very bad user experience for new HBase users. So I would recommend to pre-split the table. And then whenever you pre-split the table, you will see a performance, like significant performance improvement, at least few X. It's measurable in, like, you can just see like your regions are spread across the cluster, and your data is also like getting written at a very fast pace. So the another thing, like sometimes like users create global secondary indexes on Phoenix tables. Even though if you pre-split the main table, and let's say you have this global secondary index, you need to pre-split the global secondary index also, because when you do a write to a Phoenix table that has secondary index, in that case, you are basically doing two writes. One write goes to the main table, the second write goes to the secondary index table. So in that case, you want to make sure both of your tables are pre-split, so you don't run into hotspot at the time of seeding the table, because that will again lead into performance problem, because your main table is split, but then internally from the main table, like the region server is doing a write to the secondary index table, and that would be slower. So eventually your writes will still be slower if you don't pre-split the global secondary index table. The another settings that we leverage is Bloom filter. Bloom filters are a lightweight in-memory data structure that is used to reduce negative reads. So let's say we are doing lookup or a scan, and HBase sees like this data point can be present in 10 blocks, but if we have Bloom filters enabled, sometimes Bloom filter can specify that out of those 10 blocks, these 4 blocks definitely doesn't have the data that we are looking for, and it might be there in the other 6 blocks. So we will only read, HBase will only read those 6 blocks instead of reading all the 10 blocks. So it leads to a lot of performance optimization. By default, it's enabled at the row level, and most of the time it makes sense, because if you have static columns, you don't have any variance in column names, so you just want to try to build a Bloom filter on the basis of row values, row key. But in some case, there is another setting where you can enable the Bloom filter at the column level. What this does, it takes the row key as well as the column name, and then it starts building Bloom filters on that. We had a use case where we had this one table where it can have columns ranging from 200 to 40,000 in one row. So it has a lot of variance. It was storing data on the basis of postal codes in United States. So it varies from like the incentives. The data set is incentives. It varies from incentives can be applicable from 200 zips to entire United States. So a lot of variance in there. So whenever we do lookups for incentives, we we enabled row plus column Bloom filter, and we saw 2x performance in our reads. And now subsequently my partner Omkar is going to carry from here. Thanks.
Thanks, Anil. Hello, everyone. So I'll continue today to talk more about the table properties. I'll continue with hints. So over here, I'll talk about two hints which we have used mostly in most of the use cases at TrueCar. I'll talk about no cache, and the other one is small. So with no cache is basically we like whenever we want to avoid to get the query results to populate the LRU, at that time we can use a no cache hint. So with this, what happens is like at TrueCar, there is a use case wherein you do an ad hoc query or a nightly export of data just to send reports to an external stakeholders. So at that time, you just do a select star on a table. So at that time, you need not want to populate the LRU, and that time, so for that particular query, you can use a no cache. So what it does is basically it unnecessarily avoids churning LRU. So LRU remains like it remains as is, and this query is not affecting the LRU. The next one is small hint. So to explain more about small hint, I would like to take a sample example which I'll be covering over the next 3 to 4 slides. We did this on a data set of 2 million records, and we had a table wherein it had 50 columns. So there are 3 scenarios on which we showed how small hint actually improves the performance. First, we just did a secondary index on the main table without any hint, and what it did was we just as we know with index tables, whenever we create an index table, what it does is like it makes the row key as on the column on which we create the index as the key of the index table, and the primary key of the main table as a column to the index table. So if in our use case was to retrieve just 2 columns from the set of 50 columns, so with that it used to do a reverse lookup to the main table from the index table just to retrieve that 2 columns. And the query performance for the same was close to 10.5 milliseconds per query. The second scenario was about covered index, and with this we used a hint. So what covered index does is, basically if you can see, I have highlighted, we have this include statement wherein we include 2 columns, like column 2 and column 3. Say those are the 2 columns which I had to retrieve from the whole table of 50 columns. So I have already included that while creating the test index. So what this does is, whenever I have an index table, these 2 columns would be present in the index table itself. And then because of which I don't have to do a reverse lookup to the main table. This actually improved the performance, and the query performance was close to 2 milliseconds per query. After this, we used a small hint. So what small hint does is, I'll first tell what small hint does. It's basically, it reduces the number of RPC calls between client and server. So what happens is, with small hint, it is good if you want to do a point lookup, or if you want to retrieve a data which is less than a block size. So with that, small hint helps. And when we did a covered index with small hint just to retrieve 2 columns, the query performance improved even further, which was close to 1 millisecond per query. So as you can see, like those are the 3 scenarios which I covered in the past 3 slides. The first one being secondary index without hint, which was close to 10 milliseconds. The second being covered index with hint, which was close to 2 milliseconds. And the last being covered index with using the small hint, which was close to 1 millisecond. So as you can see, like for the same data set of 2 million records, for the same query, it actually improved the performance by 9x times. So this was a performance gain using this small hint. The next table property which I want to talk about is in-memory option. Anil has already mentioned about having the data sets. If you have a small data set, you just want to cache that data set rather than keeping it in H files. So what it does is, if you set the in-memory option to true, you basically cache that data into a data set. So this helps in fast read operations. It's close to, and we have certain data sets at TrueCar wherein we have set this in-memory option true, and the result being that all the read operations have been in single-digit milliseconds. So another use case was we had a web service. We have a web service in which we used to spin up 600 mappers, and each mapper used to load almost 1 GB of memory each time. So it's almost 600 GB of RAM occupied. So rather than doing that, we plan to have this in a centralized storage wherein we set that for that particular data set, we set the in-memory option to be true. And this actually helped us to improve the performance. And needless to say, as he has mentioned, we have to pre-split the table so that the load gets evenly distributed across all region servers. Yeah. So those were the table properties which P and Anil have covered. Going forward, I'll talk about the data modeling. So incremental keys or sequential keys, like this has been consistent, I would say, a consistent issue with normal use cases in most of the companies. So what it does is, since we have if we have to export the data from RDBMS, we just have the sequential IDs along with that. So if we create those as primary keys, those leads to hotspotting, as Anil has already mentioned. If you just overwhelm one particular region with all the client traffic, it leads to an hotspot. So the first thing it has to be done is pre-split the table. The second thing which we follow at TrueCar is, there are many solutions to avoid the issue of hotspotting because of sequential keys. The one which we follow is reversing the primary key. So if you see, whenever we create a table, we pre-split it first, and then as you can see, we have a reverse of a style ID as a primary key for the table. So what this does is, first of all, if you have a sequential key, the LSB bit is the sequential one. So it changes to an MSB bit. So it, at that time itself, randomizes it. And then if you have pre-split the table, it will evenly distribute your load across all the region servers. So that helps. So reversing can, as it is said, reversing can be done if and only if point queries are to be done. Yeah, so the other option which we have, which we considered was salting. With salting, the issue was we had to create the salt buckets right at the start when we are creating the table. So what happened is, if the data sets, like in our case, when the data set started increasing, the salt buckets created more of a problem, which led to the same slowness in the read operations. So we stuck to reversing the primary key, as that organically distributed throughout all the region servers. So reversing the primary key was better in our use cases as compared to salting. The second thing about data modeling is reading the most recent data. So this is like a primarily important use case at TrueCar, wherein we just want, this is a sample data set, but we want to read the most recent data each time if we want to query an edge-based table. So I'll explain a sample problem. So say, consider we have the sales transaction for a particular vehicle. I know a VIN for that vehicle, and I know the sale date for that. I just wanted to know what is the latest transaction for that particular vehicle. If I have a table, and for a particular VIN, I would get around almost like 10 transactions. if I just do a select star on that particular win. You can see it from the first table. I just have a win and I have a sale date. So for that particular win, I'll have two records and the sale date are one is in 2017, one is in 2018. So since HBase, as we know, is an ordered hash map, it orders it lexicographically. So what it does is basically it orders it in an ascending order. So for the same win, if my sale date, you can see that would be in an incremental order. So in case if I have 10 such records, and I want to know the latest transaction for that particular vehicle, I would have to do an order by in a descending order or in order to get the latest record. So the other way which we follow at TrueCar is we assume a future date and we do a subtraction from the current date. And we make that as a row key. So that difference from the future date to the current date would always be less for the latest transaction date. And that being, we assign that as a row key, and once, even if we do a limit one query on that particular table, I would get the latest transaction date and the latest record for that particular win. That is what you can see in the second table. Yeah. Yeah. So the next point, which we have is the EC2 instance types. Anil has already mentioned in the previous slides that we have a separate cluster, a compute cluster and a storage cluster. And so this is in specific to the storage cluster which we have, with the edge-based cluster. We earlier used to have D2X large EC2 nodes, EC2 instances, and recently we have switched to I3 2X large. This comparison chart speaks for itself, but I would say that since we have more of a read operation, like read writes, and it's more of an IO heavy operations, I3 2X large gave us a considerable improvement in performance for almost all jobs related to batch processing or streaming. As you can see, even the network performance as compared to D2X large is much more improved for I3 2X large, and that actually led to a performance improvement for most of our jobs. Yeah. So yeah, this reiterates that I3 2X large, it basically, that was the percentage. So we have both streaming and batch jobs, and both provided 25 to 120% performance improvement in our jobs. Like it basically, since it provides more of a better network performance and better read-write operations, since it uses an NV, non-volatile memory SSD, it provides a faster read-write operation with I3 2X large, which was not the case for D2X large. That's it. Thank you. Any questions?
So your question, if I understand correctly, so we have covered index with extra columns, and then we are doing the query on the covered index with the small hint. So the difference is like, so currently in HBase, so when you start a scan or something, it does 3 RPCs. Even in HBase, there is a scan called small scan. So when you put the small hint over there, so then Phoenix switches to small scan. What small scan does, it tries to get you the data in 1 RPC. So that's the basic difference between that. Any other questions? Good. Let's say if your data size that you are trying to look for is greater than a block size, then it doesn't help. Like if you know your data that you are looking for is like 1 or 2 rows, and the rows are not like in 1 MB or 2 MB, it's like very small. It should be less than block size. If you know that, then you can just like, so for point scans, point lookups and things like that, it makes sense. Or if you have a very narrow table. Sorry? Yeah. Yeah, I mean, so we use HBase as our Hadoop database. So because we don't want to put the same data in Postgres and all that, because then we have the same problem of scaling. It's like you cannot hit things like Postgres or any other RDBMS with like 200 mappers at the same time. Then you have to scale that out. So yeah, it's a very common pattern, I would say. Like it's not a like it's a very common pattern. Because as long as, so the disadvantage with reversing the key is that you cannot do range scans. So as long as you know, or all you are doing is point lookup, and you have this like data set where you are always looking for the latest data. We have few data sets where the row key is like an sequence ID that is coming from a RDBMS, and all we want to do, like it's like a hot data set within the full data set. So for that, it really helps because it distributes all your keys across the cluster. Actually, we just migrated last week, but it's all running fine. Like we migrated completely to i3. We ran it in dev for like a month, and in production we were running D2X at the same time while we were running i3s, and everyone would tell me like, "Hey, dev is running faster than prod." So uh, till now, I can't figure out of anything that is bad in i3s, because the disk is really fast, and then your networking is also better. You get more CPUs, you get more RAM, so you are just getting more stuff. It's just that the disk storage is less, which we were fine with. We just wanted better throughput. Yes. Yeah, so I'll so the question is, can you do reversing the row key and salting? I think both of them are trying to accomplish the same thing, so I would only do one. Either you can do salting or you can do reversing. With reversing, the advantage is it's more organic. I don't need to worry about data growing 10x, 20x, or 30x. With salting, I have to take care of it, even though like we haven't tried salting that much, but we just feel like it's not that much of a natural solution, because even with salting, you cannot do range scans. So you still have the same problem as you have with reversing. No, nothing. You just, yeah. So that's the advantage. Like you don't have to worry about anything. And it's like a hash function. I would call it like a hash function. My hash function is doing reverse. Given an input, it just reverses it. So I would call it like a hash function. It's like hashing.